I want to show two more examples of being able to evaluate definite integrals by substitution. So our first one, it looks like it's a fairly straightforward substitution. The second one though, maybe you have to use a little bit more intuition before you do the substitution. I'm guessing that if most of you look at this, you're going to say, okay, I try to like to make the composition be equal to the substitution. In fact, you'd be absolutely correct. So the composition in this case is what's underneath of the radical. So under the radical is 9 plus x squared. Let's let our u be equal to 9 plus x squared. I'm going to let du be the derivative, and the derivative of 9 is 0, the derivative of x squared, 2x dx. Okay. Now, unfortunately, we don't like the 2. So what we're going to do is we're going to get rid of the 2, because what you'll notice is that we have an x and we have a dx in the original integrand. Okay. So I'm going to say that du over 2 is going to be equal to our x dx. All right. So we can go ahead and substitute now. So if I were to substitute, I have my integral from a to b, because we're no longer in terms of x, we're in terms of u, so I change and make dummy variables. Instead of x dx, I'm going to have du over 2. And then finally, in the denominator, square root of 9 plus x squared becomes the square root of u. So 3 things I did there. Substituted the limits for dummy variables, substituted underneath of the radical, the original composition, and then finally substituted for the stuff that was on the outside. Now, this doesn't look like a basic integral. Let's change it into one. To do so, first of all, I'm going to factor out this coefficient of 1/2. So I get 1/2 integral a to b. Anything that's in the denominator, I make into a negative exponent if it's just a singular term. And instead of the square root of u, I'm going to turn that into u to the 1/2. So again, we have a fraction for the exponent, and because it's in the denominator, we're going to make it into a negative. So I believe that we can rewrite this as u to the minus 1/2 du. So now we can go ahead and perform the antiderivative. Remember, for a polynomial or for a singular term, in other words, if it's an x to the n, where n is some sort of value of a number, we just add 1 to the exponent, divide by the new exponent. Okay. So our antiderivative now, or integral, we have the 1/2 as the coefficient. We add 1 to negative 1/2, and we get a positive 1/2. So I get 1/2 u to the positive 1/2, and then we divide by that new exponent, which is 1/2. We don't need a plus c because it's a definite integral. We're just going to retain the dummy variable a to b. There's some good news now about this. Notice that we have a 1/2 as the coefficient and a 1/2 as the denominator. They cancel. So we like that. That's good news. The other thing that we can do is we can now back substitute for the u. Let's just go ahead and say that that's going to be our 9 plus x squared, our original substitution. So now I get quantity 9 plus x squared to the 1/2, ranging from now 0 to 4, because I'm back in terms of x. In fact, I could get rid of the 1/2 power, and I could turn it back into a radical. So let's do that. Let's now say that this is going to be square root of 9 plus x squared from 0 to 4. And now for those of you guys that are working along at home with your computations, most of you can see that this is going to work out to be a very nice number. By fundamental theorem, I'm going to substitute 4, and I'm going to substitute 0 back in for x, subtract. So I get square root of 9 plus 4 squared minus square root 9 plus 0 squared. We end up with square root of 9 plus 16, or square root 25, minus 9 plus 0, which is 9. From here, we end up with 2, don't we? Because we get 5 minus 3, or in other words, that's 2. Okay. All right, so that's our first example of a substitution, that with a substitution integral that has limits of integration with it, or a definite integral. Let's take a look now at our second one. Okay? I find that most students, as soon as you start doing trigonometry, they kind of shut down a little bit because they just don't like the trigonometry, especially combining that with the calculus. So that's one area, if you're not too good with, go back and practice it over and over and over again. All right. Now, the way I think about this is that there's 3 possible substitutions in my mind that we can make. Right? I bet if I rewrote the denominator, you could easily see the substitution. In fact, let me do that now. I'm going to rewrite this problem. Okay? So I'm not doing anything but some basic algebra. Instead of cosine cubed x, another way to write that a lot of students don't remember, or they just never saw, was you could write that as a composition of a function. In other words, cos x cubed. I bet once I do that, you're screaming at me, oh, okay, now I see. The composed factor is going to be what we've assigned to our u. So in this case, let's let cosine of x be u. And we're our wheels are spinning a little bit now, because we know that the derivative of cosine contains a sine in it. So now we're kind of getting the idea that, okay, this might be the right thing to do. Okay? Let's go ahead and do it. So I'm going to start by saying, let's let u be equal to cos of x. We know the derivative of cosine is negative sine. So we say that du equals minus sine x dx. You're probably thinking to yourself, what's the only thing I don't like about that? Well, you like that there's a sine, you like that there's a dx, but you don't like the negative. Let's just divide both sides by -1, or just multiply both sides by -1, it doesn't matter. So opposite du is our sine x dx. All right. So now we're in good shape. We can go ahead and we can substitute for sine x dx and make that our negative du. We can also go ahead and substitute for cosine of x and u. Okay. So now our integral is going to become the integral from a to b. Okay. Again, we get rid of the 0 and the pi fourths because we have now limits of integration. We put our dummy variable in there. Instead of sine x dx, that's negative du. And then in the denominator, since we have cos cubed of x and u is cosine, this becomes u cubed. At this point, this isn't as difficult to evaluate. What we want to do is 2 things algebraically. We don't like the negative attached to the du. Let's factor the negative out. So I'm going to get now the opposite of the integral from a to b. And then, just like we did in the previous problem, remember when we had the square root of u in the denominator and we moved the u to the numerator by making it a negative exponent? A very common technique in integral calculus. So now I get u to the minus 3 du. Now we have our basic power rule. I can just add 1, divide by the new exponent. This time we don't have fractions, so we like that a little bit better. So now I get the opposite of u to the minus 2 divided by minus 2. Again, I add 1 to the numerator, divide by the new numerator. That ranges down from limits a to b. What might be helpful now is to rewrite this so that a little bit algebraically so that it's a little bit nicer. Notice I have a double negative, turns into a positive. I have a 2 on the bottom, and I can move the u to the minus 2 to the bottom. So let's do this. Let's rewrite this as 1 over 2u squared from a to b. Or, instead of now in terms of u, now we can go ahead and write it in terms of x. Remember that cos x was equal to u. So now what I end up with is 1 over 2 cos squared of x. And that's now going to range from 0 to pi fourths. At this point, we just go ahead and we utilize our fundamental theorem of calculus. I'm going to substitute pi fourths back in. I'm going to substitute 0 back in. So now I end up with 1 over 2 cos squared of pi fourths minus 1 over 2 cos squared of 0. I usually get students that are a little bit trepidatious of trying to evaluate this last little component, okay? That's because they have the cos square and they have the trigonometry and it becomes difficult. What might be helpful is, remember the trick that we did almost at the beginning of this problem where we kind of rewrote it? Let's do that, and it might be easier for you to evaluate. So I'm going to rewrite this as 1 over 2 times the quantity of cos pi fourths squared. So in other words, I just basically rewrite it so that the square is now the last operation that we do after we do the cosine of pi fourths. Same thing, minus 1 over 2 cos of 0 squared. Okay. And now hopefully we can start to see that this works out really nicely. Okay. We go back and remember from trigonometry that the cosine of pi fourths is root 2 over 2. Okay? Use a unit circle to kind of help you. Pi fourths is 45 degrees. Remember at 45 degrees, the sine and the cosine values are the same. So we wind up with 1 over 2 quantity root 2 over 2 squared. And if you recall, the cosine of 0 is 1. Okay? Remember that cosine is the x-coordinate on a unit circle with radius of 1. The x is 1. So this is minus 1 over 2 times 1 squared. We do a little bit of computation, and hopefully we see that this is actually going to work out really nicely. In the denominator, 1 over 2, root 2 squared is 2. 2 squared is 4. Right. And now hopefully you're seeing that this works out really nicely. Okay? There's no radicals anymore. We know that 2 times 1 squared is just 2, so we get minus 1/2. And then we can do a little bit more computation. 2 times 2 is 4. 4 over 4 is 1. So we just end up with 1 over 1 minus 1/2, or in other words, we finally just end up with 1/2 as our answer. So what you'll notice in both of these problems is that even though they look like initially they were going to be fairly ugly, they both end up being fairly nice towards the end. So take a look back through these. A lot of the techniques and a lot of the algebra that I used are very common techniques for being able to evaluate these sorts of definite integrals using a substitution.